I want to welcome everyone to my lecture today. Before I get started today, I actually want to make an announcement. I'm done with grading. Oh yeah, I think this is not working. That is the reason. So they are not. I noticed that since 2 days lectures now. So I've reached out to them. They've not fixed it. Okay, so can you hear me now, right? Okay. Um, Before I get started today, I want to say this about midterm. I'm already done with grading, and uh, from tomorrow, I'm gonna be putting the grade because when I grade like that, I check. I want to make sure every student is fairly graded. And of course, on Friday, I'm gonna bring your booklet to the class. Okay, so I want to welcome you to another statistical topic. And of course, the focus today is actually going to be, well, we're starting chapter 9, and chapter 9 centered on the properties of point estimators and uh, how do we derive point estimators, like the method of that. But today, I'm going to be focusing on, you know, properties of point estimators. And let me tell you this. In the outline, uh, I'm going to talk about properties of a good estimator. I'm going to talk about relative efficiency and with some illustrations. Now, how do we find ourselves in a situation where we needed to investigate how good our estimator is? The whole idea started from the fact that we want to figure out the true value of a parameter. And because of the fact that we are limited by budget, we normally take sample size. We take sample from the target population. When we take sample from the target population, of course, there's going to be suggestion about what formula or method that we actually going to use, okay, on sample. Okay, that method is what we call estimator. And at times there could be more than one estimator suggested. And of course, in this class, I've walked you through, uh, you know, we've been able to see what make an estimator to be biased and what make estimator to be unbiased and so on, like that. But in a situation where we got more than one estimator, whether biased or unbiased, we may really want to compare. Maybe we were focusing on two estimator, and maybe the two estimator, let me just for start weight. Maybe they are unbiased. The two of them are unbiased, but we actually want to identify the better one out of the two. Now, if we want to do that, then we need to be able to revisit what we call properties of a good estimator. What make an estimator good? Okay, what make an estimator good? Number one, okay, one of the properties is he unbiased or not? So unbiasedness property is number one. I told you the other time, in an ideal situation, we are looking for an unbiased estimator. But I told you the other time, it may not be realistic at times, and we may settle for biased estimator. But number one property of a good estimator is that it has to be unbiased. Number two property of a good estimator is it has to be efficient. That's what we call efficiency. And what determines efficiency of an estimator is the variance of the estimator. Okay, if I want to evaluate efficiency of an estimator, then I need to put into consideration the variance. I'm going to talk about the variance if I'm dealing with the unbiased estimator. Of course, I'm actually going to talk about mean square error if I'm looking at a bias estimator. Now, I'm still trying to tell you the properties of a good estimator. Number one, I said it has to be unbiased. Number two, I said efficiency. Okay, it has to be efficient. Okay, how am I going to know whether it's efficient? When it has a lower variance. If I have two unbiased estimator, if I know the variance of the first, I know the variance of the second, and of course, I will be able to identify the more efficient one is going to be the one with a smaller variance. And if I'm focusing on a bias estimator, if I'm comparing in the class of a bias estimator, I'm actually going to be, if I want to talk about efficiency, I'm going to be comparing the mean square error. The one with a mean square, with a smaller mean square error is the one that is more efficient. Another property of a good estimator is what we call consistency. We're still going to talk about consistency in this class. We're going to focus on consistency. You know, an estimator has to be consistent. If the sample size increases, okay, we actually expect the variance or the mean square error of that estimator to be approaching zero. We're going to talk about that in this class. Then we also talk about a good property of an estimator is what we call sufficiency. Sufficiency. An estimator has to be sufficient. Okay, we're also going to talk about what we make an estimator to be sufficient in this class. But today, okay, among the properties of a good estimator that we're going to be focusing on is efficiency. Okay, that's what we're going to be focusing on today. We're going to be focusing on efficiency. Now, if you take a look at what I'm projecting, so relative, we want to talk about relative efficiency. The idea of a relative efficiency is going to come in if I actually have two estimators that are competing, okay, and I really want to look at the efficiency of one relative to the other one. Okay, now if you but right now, why am I considering variances? I'm actually considering variances because I'm dealing with the unbiased estimators. If I'm dealing with the bias estimator, I'm actually going to be talking about mean square error. Does that make sense? Okay. Now, if you take a look at the efficiency now, okay, this is a mathematical notation for that. Okay. If I want to look at the efficiency of a theta cap 1 relative to theta cap 2, I'm actually going to look at the ratio of the two variances. Okay, now this ratio can give different results. You know, I can classify the result into three that we can have. It could be less than one, or let me first start with this. It could be equal to one. When the ratio equal to one, you know what I mean? They are equally efficient. When the ratio equal to one. When the ratio here equal to one, it means the two variances are equal. Does that make sense? But what if in a situation where the ratio is greater than one? Okay, I need you to pay attention now, right? If the result you get here is actually greater than one, before you can have a ratio greater than one, it means what you have in the numerator is greater than what you have in the denominator. Does that make sense? So the only condition for me to have a greater than one here now is that the variance of theta cap 2 is greater than the variance of theta cap 1. And another condition I can have is having less than 1. When the ratio is less than 1, of course, what you have in the denominator is bigger. And you know what efficiency actually, when we're talking about efficiency, we are actually focusing on smaller variance. Any question before I move forward about the ratio? Go ahead. Exactly. If I'm dealing with a bias estimator, so it's going to be the ratio of the mean square error. But what if in a situation where I'm comparing a bias estimator with your bias? There's going to be mean square error against the variance. Or if I say mean square error against the mean square error, the mean square error of a non-bias estimator is the same thing as the variance. Does that make sense? Okay. Now I want to go into something that we apply every day, that we believe in, a scientific or statistical community. Take a look at this. I want to figure out average, okay? And they are, there are three measures of average. Three measures, we call them three measures of location or three measures of central tendency. We got mean, median, and mode. Have you heard about that before? Mean, median, mode. The three of them, they are measure of average. But how do we settle? Most of the time, we normally go with the mean, sample mean. Why not sample median? Why not sample mode? Because the three of them, they are measure of central tendency. Now, I'm going to prove to you today the reason why in statistical analysis, we prefer sample mean to sample median. Okay, we got a situation where sample median will be preferred to sample mean. But I want to show you something now. If I have, let me, I've created this. I'll give you 1 second. If I want to talk about sample mean, okay, I want to talk about sample mean, okay, then I want to talk about sample median, okay. The sample mean, if I'm talking about like, maybe talking about like y, it's going to be y bar, right? Then we also have sample median. I want to figure out an average, and there are three estimators that we can possibly use. We wrote median this way. You put something like that. Okay, now let's say these two are competing. Sample mean, sample median. These two are the estimators. Okay, and we actually want to know which one is going to be okay in terms of efficiency. If I want to look at that in terms of efficiency, I need to first, I need to know what is the variance of sample mean. What is the variance of sample median? I'm assuming median, mean, as an estimator, they are unbiased. You go into a population, you take a sample, right? You find the mean. How do you find the mean? You sum the observation divided by the sample size. If you want to find the median, you first rearrange the observation either in ascending order or descending order. Then you find the median. Does that make sense? Okay, now what I'm trying to say now is this. If I'm focusing on sample mean, we already know the variance based on what we've done before. What is the variance of sample mean? Don't forget, the variance of sample mean is sigma squared divided by n, right? That is the variance of sample mean. The variance of a random variable y is sigma squared. The variance of sample, the mean of that is going to be sigma squared over n. Now the question now, what is the variance of sample median? Okay, what is the variance of sample median. Okay, then I need you to be focused. I want to derive that now. The variance of the sample median. I go into population several times. I told you, you know, if you go into a population, you take a sample, you find the median. If 1,000 investigators should go into the same population, take the same sample size, they're actually going to have different medians. Therefore, the same way that sample mean become a random variable, the sample median also become random variable. And that is the reason why we can try to look at the expected value of the sample mean. We can also look at the expected value of the sample median. We can look at the variance of the sample mean. We can also look at the variance of the sample median. But the variance of the sample median is logical, which I'm going to figure. I'm going to show you now. Okay, just give me 1 second. I'm going to clean up. We want to figure out what is the variance of the sample median. Now, let me tell you this. In a situation where I go into a population, I take a sample size, and the sample size maybe is 2m plus 1. You know, at time you go into a population, okay, the way we calculate median is different when you have even number of observation and when you have odd. Do you remember that in your elementary statistics, right? When you have odd numbers of observation after arranging that in descending or ascending order, you're actually going to pick the value in the middle, right? And if you have even number of observation, of course, after arranging, then the two values in the middle, you add them and divide by 2. Okay. Now, if I take a sample size n, we have a sample median theorem. They're actually going to tell us we have a probability distribution for median, which I'm going to write now. Okay, the probability distribution for median. This is not in the note that I prepare, but I also want you to understand this. Okay, so that is going to be approximately n 4 raised to power n divided by square root of pi m by square root of pi m. Okay, then I'm actually going to have a capital, that I'm going to call f of x. The capital f of x that we call CDF. Okay, so I'm going to put m here, that's subscript. Then into 1 minus the capital F. If you're not seeing what I'm writing, please let me know. Okay, x. What I'm putting on that is not x bar. Okay, it's just this guy. Okay, then this guy is going to be raised to power m, then multiply by a lowercase f of x. So which means the probability distribution, okay, the probability distribution, okay, of the sample median depends on the distribution of the data. Because let me tell you this. If there's an outlier in the data set, according to Benkamp in 1982, outlier is a data point that is not consistent with the rest. If there's an outlier in the data point, of course, that could induce skewness that will make the distribution of the data set not to be normally distributed. And we prefer to use sample median in that situation compared to sample mean. But when the distribution of the data set is normal, of course, any of that can be used. Because when the distribution is normal, the mean, the median, and the mode, they're actually going to agree. But the best, the most appropriate one is actually going to be mean. But median can also be used. Okay, now this is the probability distribution. But you know what? We want to have an assumption now. We want to have an assumption in a situation where the population distribution is normal. And don't forget, we're told if the distribution of data set is normal, mean, median, mode, what happened to them? They agree, right? Okay. Now, if they agree, then which one are we going to choose? Why do we choose sample mean against sample median? Then that is what I want to show you now. Okay, so I'm going to show you now, like I said, Now, based on the formula that I show you right now, we got a formula. We got a formula for the variance of the sample median. Please write this. The variance of the sample median, okay, the variance of the sample median is actually 1 over 8m. 1 over 8m. This guy is going to be m. Let me write very well. Give me 1 second. I'm going to erase this guy now. Then I'm going to write that. Okay, so 1 over 8m. Okay, then f of mu. F of mu. But that very mu has to be median or squared. Now, this is the formula for the variance of the sample median. Okay, which means this formula depends on what? F of mu. Does that make sense? Okay, now let's say we assume that the median has a normal distribution. If the median has a normal distribution, okay, median will be equal to the mu, right? Now, let us write the normal distribution. You know, in the normal distribution, the f of x, okay, f of x is actually 1 divided by square root of 2 pi sigma squared, right? Exponential raised to power negative 1 over 2. Okay, I'm actually going to have x, right, minus mu, okay, over sigma, right, or squared. You know, this is the probability distribution of a normal distribution. Okay, now when data set is normal, okay, then this guy here is actually, I'm going to have mu. When I plug in mu, what is going to happen to the exponential aspect? The exponential aspect now, if I write f of mu, if I write f of median, you know here, this guy is a median, right? And mu and median will be the same for normal. Then in that situation, I'm actually going to be left with 1 over sigma square root of 2 pi. This guy now. You see that? This guy is what I'm going to plug in into f of mu or squared. Is there anyone who doesn't understand what I've done here? Which means whatever distribution, okay, of the data set, okay, you need to for derive that before you're going to plug that in the variance of the median. Now, if that is what I have, what I'm just going to do is wherever I see f of mu, okay, I'm going to plug in 1 over sigma divided by 2 root pi. Don't forget the other guy with mu, with this, equal to this, right? That entity is going to be exponential response 0, which is 1. I'm only going to have this guy. So by the time I plug that, I'm now going to plug that guy in here. Okay, when I do that, I'm going to write the final answer now, so for you to see. So the final answer now, the variance of the sample median, the variance of the sample median, okay, by the time you plug that in, is going to be pi. Okay, when you simplify algebraically, it's going to be this divided by 4m. If you simplify, okay, you're actually going to have pi sigma squared divided by 4m. Okay, so this is what you actually going to have. Now, if I now want to consider central limit theorem, okay, we also consider central limit theorem when we're focusing on the sample mean, and under central limit theorem, we expect that when sample size is sufficiently large, what happens? The probability distribution of the sample mean, what does it become? It follows normal distribution. Okay. Now, because of that, if I also want to bring that idea of the variance of a particular random variable in that regard, where the random variable is actually mean, okay, I'm actually going to have sigma squared, right, divided by n. Okay, sigma squared divided by n. And if I have sigma squared divided by n, initially when I started, I equate n to be what? 2m plus 1. Okay, so 2m, okay, plus 1. Now, I needed to take a look at this guy now. Okay, I needed to take a look at this guy now. I have the variance of x in the sigma square over n, which is equal to that. And let's say I want to write this guy now in terms of the variance of mean, of the sample mean. Let me say this again. I want to rewrite the variance of the sample median in terms of the variance of the sample mean. Okay, now this is what I'm actually going to do. I got the variance, okay, of the sample median, okay, the variance of the sample median, okay, which is pi. I'm going to go back, like I'm talking about this guy now. This guy, let me just say that guy equal, okay, pi, okay, over 4m, okay, 2m, 2m plus 1, okay, then the variance of x bar. Let me see how I'm going to write that. Now, I needed to focus on this. Okay. If you take a look at, let me write that so that it doesn't look like, let me write pi over 4m. Okay. Pi over 4m sigma squared. Okay. Equal. Okay. Pi. Okay. Divided by 4m. Okay. 2m. 2m plus 1. Okay, then variance of x bar. Okay, now I need you to take a look at what I just wrote. Variance of median, you see pi sigma square over 4m, right? Now, pi over 4m, what is sigma squared? The sigma square, if you come back here, this is for the mean, right? You see the variance of the sample mean is what? Sigma square over 2m plus 1. If I want to substitute, if I want to make sigma squared here, this is the formula. If I want to make this guy, the subject of the formula is going to be variance of x bar multiplied by 2m plus 1, and that is what you are seeing here. Any question on how I derived that? Any question? Now, I've been able to express variance of the sample median in terms of the variance of the mean. Now, in that situation now, I can now say when n is large, what happened? Okay, when n is large, what happened? Like where we are now, we are actually, let me clean this one. Okay, so I'm gonna clean this guy now. Okay, and of course you know where we are now. Okay, where we are is the variance of the median equal this guy here. So what I can do now, I can actually resimplify. If I have pi divided by 2, you know, from this pi, you know, there's a 4, right? And I write 2m, mathematics now, 2m plus 1 divided by 2. You can see the 2 here, the 2 times 2 is that 4, right? Then the variance of what? The variance of sample mean, don't forget this guy here, the variance of sample median. Any question? Any question on how? Now, what I want to work on now is working, oh, sorry, there's an m, right? You see, there's a 4m, right? If I split, it's going to be pi over 2, okay? And that over m. Now, I want to work on this guy now. Okay, for situation, I want to apply central limit theorem. Central limit theorem for n tends to infinity. And don't forget, n is 2m plus 1. Does that make sense? If n tends to infinity, m also tends to infinity. Now, I want to apply that loss of infinity on 2m plus 1 over 2m. Can somebody tell me what it's going to become? If m tends to infinity and I have 2m plus 1 over 2m, what is it going to become? Can somebody tell me? 1. That guy, 2m plus 1, because you're actually going to divide everything by 2m, 2m by, 2m by 2m. And don't forget, m is a very big number. Where you have m in the ratio is going to tend to 0. So at the finally here, okay, when central limit theorem applies, what am I going to have? I'm going to have pi over 2. So let me clean this so that you can see very well. So when n is large, applying central limit theorem, okay, just like what I said. So what am I going to have now? I'm now going to have the variance, okay, the variance of the sample median, the variance of the sample median, okay, the variance of the sample median will be pi over 2, okay, but not exactly, is approximately pi over 2, then variance of the sample mean. If I want to know which one is greater, then I need to consider this fraction. Okay. What does pi over 2 give us? You know, pi is 22 over 7, right? 22 over 7 divided by 2. That will give you 1.57. Does that make sense? Okay, so which is going to be let me use my calculator. I'm going to use my calculator. So 22 divided by 7 divided by 2. Yeah, it's going to be 1.5, which means, okay, the variance of the median is 1.5 something variance of the sample mean. Which one is larger? Then the variance of the median is larger. Now, and that is what's going to lead us to what we now want to do now. Take a look at this. You know, some of you may be wondering, how do they get this? Now you know that 1.57 is the square of this guy. You know, you can see they put 1.2533 square, right? What is 1.2533 squared? You actually it's going to be 1.5. That is going to be pi over 2. Does that make sense? Now, what do you see? What do you see in the numerator? That is the variance of the sample mean. What do you see in the denominator? Variance of the sample median. At the end of the day, what do we get? Less than 1. 0.6 something is less than 1. And when you have less than 1, right, when the ratio is less than 1, so out of the denominator, it means this guy is greater. It means the variance of the sample median is greater than the variance of the sample mean. And because of that, we actually, you know, when you want to look at the from the efficiency angle, because the, this relative efficiency is less than 1, that actually favors sample mean. Okay, and that was why if I want to interpret that guy, you know what it means? The variance of the sample mean is approximately 64% of the variance of sample median. Variance of the sample mean is approximately 64% of the variance of the sample median. So which means the variance of sample median is bigger than the variance of sample mean. Any question? And this is the reason why in statistical analysis, we prefer sample mean to sample median, but in a situation where the probability distribution of the underlying population is normal. If it is not normal, then I'm afraid it's not going to be sample mean. You know why? Sample mean is sensitive to outlier. Okay, now I want to go into something more. Take a look at this. You have two unbiased estimator. It's another example. Okay, theta cap 1 equal to 2y bar, and theta cap 2 is n plus 1 over n times the maximum order statistics. Okay, and they want you to find the efficiency of theta cap 1 relative to theta cap 2. Now take a look at this. You start with the way what we normally do, but what is the underlying distribution? Please, underlying distribution is very, very important, even though probability distribution has a tendency of changing, like the distribution of the sample statistic could change, could convert to normal when central limit theory applies, but it is very, very important to know the underlying distribution. The underlying distribution here is uniform. And what was the interval here? 0 and theta, right? That is the underlying distribution. Now, if you're given an estimator, okay, the estimator you're given here is actually 2y bar. Theta cap 1 equal to 2y bar. You need to follow first. What is the expected value of y from the uniform? uniform, expected value of y for uniform is a plus b over 2. Your b is theta, your a is 0. So your expected value of y will be theta over 2. What about the variance of y? B minus a all squared over 12. You remember if the variance of the uniform, okay, you have that. Then you can now find the expected value of theta cap 1, starting from where? The unbiased angle, okay? What is the expected value of 2y bar? 2 expected value of y bar, okay? 2, what is the expected value of y bar? Mu. What is mu? The mean that you got here, the theta over 2. You plug that in, what happened? The first estimator, theta cap 1, is unbiased. Why is it unbiased? Because the expected value of theta cap 1 equal to the population parameter. Now, after getting that, the next thing is to investigate the variance. Okay? You investigate the variance. The variance of 2y bar. Mathematically, that will be 2 squared variance of y bar. What is the variance of y bar? Is going to be variance of y divided by n. For normal, sigma squared over n. That sigma squared is the variance of the random variable x or y. Now, what is the variance of y? You've already gotten that from here. The variance of y theta squared over 2. By the time you plug that in, what is the variance of the estimator now? The variance of the theta cap 1 now is theta squared over 3n. So you've gotten both the mean of the theta cap 1 and the variance of the theta cap 1. Then the next thing that you want to do now, then you want to, you want to be able to analyze that of the second estimator. Now, in the second estimator, you've been told that, the second estimator is this. Well, give me 1 second. This is the second estimator. The second estimator has something to do with the maximum order statistics. For maximum order statistics, I told you the other time, whether minimum or maximum, we got a distribution for them. You don't need to derive it. The distribution for the maximum, do you see the formula I gave you the other time? For maximum, what do you need to do? In the distribution for maximum order statistics, there's an uppercase f, CDF, there's a lowercase. Okay, the f of y, which is lowercase, is the underlying distribution, uniform. Okay, here, when you take a look at the interval given, right? Uniform is 1 over b minus a, right? If you remember from lower level statistics, here your b is theta, your a is 0, then the lowercase f of y will be 1 over theta. That is why you see 1 over theta. Okay, that is why you see 1 over theta. Then what is the CDF? The CDF of that, if I have 1 over theta, it's going to be just y over theta. That is why you see this, y over theta. Okay, then by the time you plug that in the formula of the maximum order statistics, then you're actually going to have this guy here. When you have that guy, what you do need to do? Oh, I need the expectation of y, and I also need the variance of y using the distribution. Take a look at what I'm going to do now. Oh my God, that is what I want to do here. That is what I'm trying to do now. Take a look at this guy. Expected value of y. I'm using that distribution. Okay, the maximum order distribution that I derive, which is going to be integral, okay, y, okay, f, or that distribution, the y, then when I do that, that is going to give me this guy. Then because I want to find the variance, I need to find the expectation of s squared so that I can use the formula here, and finally I got the variance. Okay, and after that, I can now investigate for efficiency. Now, if I go back to the variance of the theta cap 2 now, don't forget the theta cap 2 is this. And the variance that you got, okay, n plus 1 over n is a constant, right? When you come out, you're actually going to have this. Then this guy here is the variance that you got from the other statistics. Okay, you're actually going to plug that in. When you simplify, you got a lot of mathematical work to do. This is going to be the variance of a theta cap 2. What is the next thing to do? Is to find the ratio of the variance of theta cap 1 and the variance of theta cap 2. Okay, which is what I'm trying to do here. This is the variance of theta cap 2 that I got from here and the one that I got before. And when I simplify, you see why you do algebra in high school? Okay, 99% of what we do in math is algebra. Okay, now this is what you go. If I go 3 over m, 3 divided by m plus 2, when sample size equal to 1, can somebody tell me what happened? When sample size equal to 1, when you take a 1 sample size, what happened? The ratio is going to be 1. But can you take sample size 1? No. You're actually going to take larger than sample size 1. Now, from 2 and above, that was why I said when n is greater than 1, what is going to happen to this? It's going to be less than 1. When it is less than 1, which one is greater? Which variance is greater? When the ratio is less than 1, okay? When the ratio is less than 1, the one that is actually greater, that's why I said this efficiency is less than 1 if n greater than 1. And which means theta cap 2 has a smaller variance, okay? Because that is less than 1. Now, these are likely questions from the textbooks. You can try this. Because by the time I'm going to be giving assignment, they're going to come from here. Take a look at that. Any question? I think there are a lot of questions, a lot of exercise that you can actually try. But let me tell you this. You need the knowledge of calculus and the knowledge of algebra. You need to revisit them. Any question? Like I said, on Thursday, your grade will be posted, and on Friday, I'm bringing the exam booklet to class. Make sure you all stay safe and have a lovely day. Bye for now, everyone.